Hello, STEM learners. So today I'm going to cover this question where the Queen of May is sailing due east at 10 knots. And so let's grab this information. Sailing due east at 10 knots. The first thing we want to do to solve this is to just draw a picture. And so let's draw our vector, which represents the Queen of May sailing due east. And we'll call this V1. And then the next piece of information in this problem is that the blue star is sailing 30 degrees west of north at 15 knots per hour. And so if we look over here at our coordinate axis, north is pointing up, and then west of north is this direction. And so it's going 30 degrees west of north at 15 knots per hour. And we'll label this V2. And we'll say 15. And V1 is equal to 10. And so whenever you have a vector like this, you can break them up into their components. So let's just start and think about V1. So V1 is equal to 10. Now, if we want to break V1 into its x and its y components, well, V1 is actually just moving purely east. So that means it's only moving in the x direction. And actually, the y component would just be 0. So that one is easy. But now, what about V2? So we know that V2 was 30 degrees. And if we break it up into its component vectors, this here would be V2y, and this one here would be V2x. So we can see, or we know from sort of trigonometry rules, that V2x is opposite of the degrees. V2 would be the hypotenuse, and V2y would be adjacent. So using this information, we can actually write out our trigonometry rules to break V2 up into its components. And so we know from trigonometry that sine of the 30 degrees would be equal to opposite over hypotenuse, which would be V2x over 15. And so then we can move the 15 to the other side, and we can write this as V2x equals 15 sine of 30. And if we get our calculator out, we can calculate this. So we get 15 times sine of 30 in our calculator, and I get 7.5. And so we can set up an identical rule, but now for V2y, and say, okay, cosine of 30 is equal to V2y over 15. And so we can rearrange this and move 15 to the other side, say V2y equals 15 cosine of 30. And if we get our calculator out, we get that this is equal to 13. And so why have we gone through all this effort into breaking up our two vectors into their x and y components? Well, let me show you. The reason is that when you have two vectors like this, you can actually find the resulting vector between them, like this. And that resulting vector for this problem would be how fast that they are separating. I'm just going to label this VR. And the resulting vector is actually equal to the x, like if we want to find the x component of the resulting vector, it would be like this. So we'll label this VRX. And it is the sum of the x component of the first vector and the x component of the second. And then I can also draw V2, or sorry, VRY. So let me just move this. This would be VRY. And you can see that the y component of the resulting vector is the sum of the y component of V2 and V1. And so let's just go ahead and write this out. So VRX, so our resulting vector, is going to be equal to V1x plus V2x. And we know from over here that V1x is 10 and V2x is 7.5. So if we calculate this out, we'll get that VRx is equal to 17.5. And then we can write the same thing, but for VRy. And we know that this is equal to V1y plus V2y. And so over here, we see that V1y is 0. We'll plug that in. And then V2y, we calculate it out to be 13. So if you sum those two together, VRy is equal to 13. So great. So now we just need our final resulting vector. You might know from vector rules that you can find what a vector is from the components by doing the square root of each component squared. So this rule here comes from Pythagorean's theorem. So all we need to do now is plug our v1x and v2x into the rule. So we get 7.5 squared plus 13 squared. Now, if I grab my calculator, and I can calculate the square root of 17.5 squared plus 13 squared. And I get 21.80 knots per hour. And then that's it. This here would be the final solution to this problem.